So good morning. Good morning. It's a real pleasure to welcome all of you to our very first AI Summer School. So one of our goals is to convey to you our excitement about AI research can and is making a difference to some of the toughest problems we face today as humans. And at the same time, there are so many outstanding challenges associated with the AI technology itself, which are opportunities to do interesting research. So let's start with some of the challenges we face right here in India. 50% of our population derives its livelihood from agriculture, and yet agriculture accounts for barely 16% of our GDP. Our crop yields are much lower than much of the world, and we are very inefficient in the use of water for agriculture, consuming close to 80% of the fresh water for agriculture, and in many places we are running out of fresh water. Our farmers don't have access to basic information and services that you and I take for granted. They can't get reasonably priced crop insurance, and so many farmers end up committing suicide when they face a crop failure. Looking at health, we have a somewhat poor infrastructure for public health. We don't have enough doctors to serve our population. Most of our primary healthcare centers have no medically trained doctors, only partially trained healthcare workers. Looking at education, we have a very young population, but need our young people to have the right education and skills so that they can provide the true demographic dividend rather than becoming a burden. I would look at all of these challenges as really an opportunity to make a difference. I feel we are at a very special moment in computing history where compute power is available in such abundance that things we used to think of as science fiction are now possible, and which has led to a resurgence of the field of AI, and in particular, deep learning, the modern reincarnation of artificial neural networks, which is impacting each and every aspect of how the world is run. So while these are technologies are changing the world, there's so much more to do on improving the core technologies themselves. The hunger for huge amounts of training data, the fairness issues, the biases that these algorithms can perpetuate, the black box nature of many of these algorithms. Uh, so, so we have a fantastic lineup of speakers who are going to take you through their own research and drive discussions on open research topics. So I strongly encourage you to take the time to immerse yourself and engage in these discussions over the next 3 days as if you were physically present. And we promise you it will be worth your investments. So we are fortunate to have none other than Jeff Dean deliver the opening keynote, and it's a real pleasure to welcome and introduce Jeff. Jeff is a senior fellow at Google and leads Google Research. He's well known for his work on MapReduce, Bigtable, Spanner, LevelDB, Disbelief, which was refactored into TensorFlow. So in a nutshell, Jeff designed and implemented large parts of the company's advertising, crawling, indexing, and query serving systems, along with key pieces of the distributed computing infrastructure that underlies most of Google's products. Jeff holds a PhD from University of Washington. He's received many honors, including the ACM Prize in Computing, which was then known as ACM Infosys Foundation Award in Computing Sciences in 2012. He was elected to the US National Academy of Engineering in 2009 and is, of course, an ACM Fellow. Jeff has also inspired a whole series of jokes that may remind this audience of Rajinikanth jokes that you always hear. And to give you a few examples of Jeff Dean facts, Jeff Dean invented MapReduce so that he could sort his fan mail. Jeff's resume only lists things he hasn't done because it's shorter that way. So taking a cue from that, I will stop listing Jeff's accomplishments because that would leave very little time for his actual talk. So over to you, Jeff.
Great. Thank you very much for that kind introduction, Manish, and I'm very excited to be with you all today. Good evening to me, good morning to you all, and I'm sorry we can't get together in person. I hope everyone is staying safe. I know the world situation is pretty interesting these days, and I hope we all get through the COVID pandemic. But on the bright side, I can sit in the comfort of my home and speak to you all. So with that, I'm just going to launch into the slides, and this is going to be a rather rapid fire talk that kind of covers a pretty broad set of work going on at Google Research. Let me see, let's go ahead, share my screen. Here we go, the usual dance with these things. Fantastic. Can you all see my slides? Great, I will assume so. So I'm going to talk to you about the use of deep learning to solve challenging problems in the world. Actually, some of them that Manish touched on in his introduction. But first, I want to highlight the kind of inflection point we're at in computing, where the field of machine learning is really creating tremendous interest because we're able to now use machines and use learning algorithms to solve problems that we don't know how to solve in any other way. And this graph kind of shows you the trajectory of interest in machine learning in terms of the number of research papers being published in that field, posted on arXiv, a popular preprint hosting service. There's now more than 130 new machine learning papers being posted every day as of the end of 2019, and it's likely gone up even now. So I don't envy students trying to keep up with this field. No one can hope to keep up with this flood of papers. So you have to kind of identify some areas that you really care about and keep up with those, and kind of keep a little bit of interest in some of the other areas, important developments in areas that are a little bit farther from your particular area of interest. But don't feel bad. Everyone feels a bit overwhelmed in the amount of new research coming out every day. So deep learning is actually this kind of subfield of machine learning that is the modern kind of reincarnation of artificial neural networks, which are actually a relatively old style of machine learning. They were developed in the 70s and became kind of popular in the late 80s and early 90s. I actually got excited about them at that time when a lot of people were starting to get excited because they seemed to be able to solve interesting toy scale problems in new ways that didn't seem to be solvable in other ways. And so I was pretty excited. I felt like if we just had a bit more computational power, we could solve really interesting problems. And so I did an undergraduate thesis on parallel training of neural networks, taking the 64 processor machine we had in my undergraduate school's department and implementing some machine learning neural network training algorithms there and parallelizing them across the 64 processors. I was just convinced that if we could get 64 times as much processing power, we could do amazing things. I was a bit wrong. It turned out we needed like about 1 million times more computational power. But starting about 10 years ago, thanks to Moore's law, we started to actually have that amount of computing power in sort of an accessible form for people. And so the same basic algorithms that showed promise on toy scale problems in the 80s and 90s suddenly started to show really interesting results on sort of interesting real world problems in about 2008, 2009, 2010. And the key benefit of deep learning and neural networks is that the system can take in very raw forms of data, like the pixel values of an image, the red, green, and blue pixel values, and through a layered approach can learn higher and higher levels of abstraction that build on lower levels of abstraction that are all learned throughout as one continuous part of the training process. So lower level features learn things like edge detectors at different orientations. Middle level detectors learn combinations of those. So is that a corner or is it a splotch of green with an edge on one side? And then higher level features learn kind of, oh, does that look like a cat ear or a cat eye or things like that? And then the system can be trained to predict lots of different kinds of things. And so, for example, they're very flexible in terms of what you can train a neural network model on with relatively the same training algorithms. So you can train an algorithm to take in pixels and produce, a categorical output of leopard or one of thousands of other categories. You can train it to take in an audio waveform of, some utterance and what is being said, and then train the model to basically emit a transcript of what is being said. How cold is it outside? And that's speech recognition. And you can train the system to take in text in one language, hello, how are you, and produce text in another language, bonjour, comment allez-vous. and that's machine translation. So in the past, all of these different disciplines, speech recognition, machine translation, computer vision, tended to have their own specific algorithms and so on. But with the beauty of deep learning, we can actually use very similar algorithms to solve all of these different problems. You can even kind of combine these things. So you have a nice vacation photo that I took of a cheetah sitting on a car, and the model can produce captions like a sentence describing that image rather than just a categorical output, a cheetah lying on top of a car. So just to give you a sense of the vast improvement we've had in the field of computer vision as one example, in 2011, Stanford every year runs a contest called the ImageNet Challenge, where you're given a bunch of full color photographs, and each one has been classified into 1,000 different categories. And the goal of your model is to produce the correct label, correct one of the 1,000 categories for the image. And the winning entrant in 2011 had an error rate, did not use deep learning, and used other kind of simpler computer vision algorithmic methods, and got 26% error. And we know that human error on this task is about 5%, because it's actually a pretty difficult task. It's not like humans will get 0%, because you have to be able to identify 40 different breeds of dogs among the 1,000 categories, and that's pretty hard for the average person. They don't necessarily know all the breeds of dogs. And then in 2016, the winning entrant used deep learning. Actually, in 2012, Alex Krizhevsky, Ilya Sutskever, and Jeffrey Hinton entered the contest and got a huge reduction in error rate using a deep learning-based approach. And they were the only entrant in 2012 that used deep learning. The next year, something like 28 of the 30 teams used deep learning. So this basically, their results in 2012 revolutionized the field of computer vision, where everyone suddenly switched to using deep learning-based methods. In 2016, the winning entrant got 3% error, which is pretty phenomenal. So we've gone from, in 2011, computers not being able to see, to all of a sudden today, computers can see, and in some cases, for particular tasks, can see better than humans. So this is pretty amazing and revolutionary. If you think back to the time in sort of evolution of animals, the time when animals evolved eyes was the time of great change, I suspect. And so we're at the same point in computing, where now computers can suddenly see and perceive their environment in new ways that they never used to be able to do. And so this has dramatic implications for what we expect and hope that computers will be able to do. All of a sudden, many things seem possible. And I'm going to take you on a bit of a tour through this list of the US National Academy of Engineering in 2008 decided to publish a list of 14 grand engineering challenges for the 21st century. And so they got a bunch of people together, experts, and came up with this list of 14 things. And I think if you look at this list, you'd agree that these are really grand kind of challenge problems. And if we were to make progress on one or more of them, the world would be a better place. All of a sudden we'd have, the ability to have renewable energy produce most of our energy. People would have, better healthcare, better medicines. We'd better understand the brain. We'd have, advanced personalized learning, which can help with education, and so on. So within Google Research, we actually have work going on in all the things listed in red. And I'm going to touch mostly on the ones listed in boldface red, the two at the bottom of the left column and the one on the bottom of the right. Okay, so restore and improve urban infrastructure. This is one of the grand challenges, and we are on the cusp of having something pretty amazing, which people have dreamed about for a long time. But the fact that computers can now see is really going to make what's going to make this possible in the near future. So this is designing and operating autonomous vehicles. So cars that can drive themselves over the same streets that human-driven cars operate on and obey all the traffic laws, which, depending on where you are in India, is a flexible interpretation of traffic laws. But being able to understand all the road signs that they're seeing, the behavior of other vehicles, take all the raw sensors that these kind of autonomous vehicles have, which come from a spinning LiDAR that gives kind of a 3D point cloud, and a bunch of cameras all over the car, some radar, and to fuse that all together into a high-level representation of the scene around them really is kind of what deep learning is really good at. And so we can take all this information and produce this amazing view of the world, and then allow us to make good decisions in an autonomous vehicle operating environment. Similarly, robotics is going to be something that is dramatically changed by the fact that computers can now see. If you want to have a robot operate in the world, it's obviously going to be much better if it can see what's going on around it. And so in 2015, there was a challenge task where the goal was to grasp an unseen object, an object that the robot had never sort of experienced before. And the state of the art at that time was 65% grasping success rate, which is pretty bad, actually. It means if you try to pick something up, a third of the time you fail. And so in 2016, our robotics research group did a bunch of work to effectively use parallel data collection. So we got a room with about 10 different robotic arms and enabled them to practice picking up objects from random assorted bags of different kind of toys and small tools. And then we could pool the training data that they practiced every night and train a new model, and then every day push out a new model and have all the robots learn from their collective experience. And this enabled us to get the grasping success rate up to about 78%. And then in 2018, with a bit more work and some more sophisticated reinforcement learning algorithms, that team was able to get up to a 96% grasping success rate. So similar trajectory to what you saw in computer vision, going from 65% success to 96% success. All of a sudden, things that didn't seem possible or would be very hard seem plausible. Like you could stitch together, grasping something, moving it over here, dropping it over there, and have some hope of a robot being able to repeatedly do that. The other thing we'd like our robots to be able to do is to learn new skills quickly. And so one of the things we're working on is how can we have robots learn from demonstrations? And so here's one of our AI residents in a demonstration video demonstrating something with the robot. And on the right, you see some demonstrations of humans pouring stuff into different kinds of cups. And the robot gets to observe about 10 short clips of people pouring things, and then gets a reinforcement learning-based reward of how much stuff goes into the cup. And after a few trials, so 15 minutes of experimentation plus those short videos, the system is able to pour reasonably successfully, maybe at the 4-year-old child level, not at the 8-year-old child level. But that's pretty good considering to what you'd have to do to a robot in a sort of hand-coded control algorithm sense to get it to pour, and that kind of approach wouldn't really generalize to new settings and new angles and new kinds of cups and so on. So we're pretty excited about this general area. Another area that we're excited about is the potential of using machine learning for healthcare. And so one of the hopes is that you can use machine learning to train on data that experts have sort of evaluated and labeled, and then use machine learning to then be able to generalize that to new settings and bring that world-class expertise to everyone at lower cost. And actually, we're doing some of this work in India. So one of the diseases that we've chosen to focus on, the imaging problems, is the diagnosis of a disease called diabetic retinopathy. And so I'll walk you through an example. So we chose this because it's the fastest growing cause of preventable blindness in the world. And screening can prevent blindness. Basically, if you catch this disease in time, then it's very treatable. But if you don't catch it in time, then you lose full or partial vision before it's treated. And the screening is really specialized, so most doctors can't do it. You need an ophthalmology background and training in order to do that. And in India, for example, there's a shortage of more than 100,000 eye doctors. And as a result, that's not enough to even do this regular screening that people need. And so 45% of patients lose some vision, full or partial vision, before they're diagnosed. And here you see a picture at the Aravind or Sankara eye hospitals where we have deployments of people waiting in line to get screened. And it turns out in the same way that a neural network can learn to take general images and predict 1 of 1,000 categories, it can also learn in a similar way from a collection of retinal images and that have been labeled by ophthalmologists as 1, 2, 3, 4, or 5 are sort of the categorical ways in which they assess this, from no diabetic retinopathy to proliferative. And you can just train on that different data set with roughly the same kind of model, and you get a model that is pretty high quality. It's basically on par or slightly better than the average board-certified ophthalmologist. And so all of a sudden, you now have something that on a desktop GPU card can evaluate tens or hundreds of images per second with the quality of an ophthalmologist. You can actually even do better if you get the images labeled by people who have more training. So instead of a board-certified ophthalmologist, if you get a retinal specialist, someone who has additional advanced training in retinal disease, and you get 3 of them together to then agree on a single label. So rather than getting independent assessments, you use what's called an adjudicated protocol, where 3 retinal specialists get together and they come up with a single number together through a discussion process. If you get the image data labeled that way and then train on that data, you now have a model that is on par with retinal specialists, which is kind of the gold standard of care, and better, considerably better than board-certified ophthalmologists. And there's a whole bunch of other applications in healthcare. This is just a sampling of many of the other projects we're working on. Interpreting chest CT scans to detect lung cancer, using data in medical records to make predictions about how, what diagnoses make sense, or what medicine is appropriate in which setting, or is this patient likely to develop diabetes in the next year, and if so, maybe you should have some, some way to reach out to them and encourage them to change their diet, predicting acute kidney injury, many, many kinds of applications like this. So many of the advances that we're seeing over the last bit depend on being able to understand text. So I'm going to walk you through some of the evolution of text understanding models in the past 3 or 4 years. So prior to all this work, the sort of state-of-the-art text models were recurrent neural networks, where you had a system that had some internal state and could then look or observe the next word or the next token and do some processing to update its internal state, and then would move on to absorbing the next token. And the problem with that is that's a very inherently sequential process. Each token you need to sort of serialize and update the state before you go on to the next one. And so in 2017, a team of our researchers worked together to come up with a new kind of approach to this, where essentially you could process lots of tokens in parallel and then use an attention mechanism to pay attention to tokens to your left that made sense to focus on, rather than having this serial process of it 1 token at a time. And so through this, the system was able to get significantly higher translation quality scores. So BLEU, as it's called, is a measure of translation quality. And so this is a transformer model applied to language translation. And what you see is that the transformer model was able to achieve significantly higher accuracy and use much less compute in order to do that, because it's able to have this attention mechanism and update its words in parallel. It's much more computationally efficient. So roughly 10 to 100x less compute and higher accuracy. So that was a pretty big improvement. And then another research team within Google saw that work of transformers and built a system, a new kind of approach on top of that is called BERT. It's a bidirectional encoder representation from transformers. So each of these blue circles here is kind of the core piece of the transformer model. And here we're going to allow the model to look not just to the left, but to the left and to the right for contextual cues about what kinds of things it should predict. And so one of the really cool things about the BERT model is the way it's trained is actually remarkably simple. So you take some piece of text and you randomly drop some of the words. And now you force the model to try to guess the missing words in the right positions from the contextual cues that it has of the remaining words. And so that is effectively the training process. You drop some random words, you ask the model to reconstruct the missing words, and then if it gets it correct, great. If not, you can get an error signal, a gradient, that you can feed back through the model so that the next time it sees similar kinds of contexts, it will make a more informed prediction. And so one of the neat things about BERT is a thing that works extremely well is you can pre-train a model on large amounts of self-supervised text. So if you just have lots and lots of text, you can do this fill-in-the-blanks training approach by just dropping little bits of it and training on billions or hundreds of billions of tokens. And then in step 2, you maybe have a more focused language task where you only have 10,000 examples of something where you're trying to take a sentence and predict, is the sentence saying something nice about someone or something negative about someone, maybe. And often that limited amount of training data doesn't do very well, but with this pre-training approach where you've trained on billions of words of text, you can really get a lot more out of each example in the limited training example tasks that you do have. And so this actually works remarkably well. Another thing we're pretty excited about is having large models, but only sparsely activating them so that you don't turn on the entire model on every example. And the motivation here is that you want really large capacity to remember lots of stuff about, hundreds of billions of tokens of text, but any given example should only activate a tiny fraction of the model. So maybe you have a part of it that's really good at scientific text talking about biology, and another part that's good at Shakespeare. Maybe those two parts don't need to be on for the same example. And so one of the things we're excited about is per example routing. So this notion that you have a whole bunch of experts, each expert has lots of parameters to remember stuff, and you have a lot of experts, but where you have a gating network that is learned, so this green bit, where the gating network learns to activate the appropriate experts given the kind of representation of the example that's coming from below in the model. And with that, you can turn on just 1 or 2 of the 2,000 experts. So you have a relatively low computational cost for doing that, but you have this large capacity. And this actually works remarkably well. So the top row here is a model with this 2,000 experts, and the bottom row is something without the experts. And what you see is the blue score, the test blue score is higher for the model with experts, despite the amount of computation per word being less than half as much, and the training time being roughly 1/10 as many GPU days. So that's pretty exciting. And then people have combined that instead of with an LSTM, as that original work did, with a transformer model, and have gotten really good results on a language translation task using transformers and very large, sparsely activated models. So this is a standard transformer. You can apply the same mixture of experts style trick to it, where you now have a whole bunch of experts that are in the middle of the transformer stack, and you learn the gating function and activate just a handful of the experts. And there, what we're able to see is that we can get 7 blue points of improvement over a very strong baseline with only 1/10 the amount of training cost. So again, similar kind of results as what you saw in the earlier thing, and pretty great. And the nice thing is the blue score improvements are larger for languages where you have fewer examples. So the right-hand side of this graph has fewer examples per language, and the left-hand side has many examples per language. But you see generally that there's a big improvement over the baseline production system, which is at 0 here, and a big improvement over the densely activated system where you don't have any mixture of experts, any experts at all, and you just fully activate the model entirely on every example. Okay, engineer the tools of scientific discovery. So that's another exciting area. And one of the things is that if you believe that machine learning is going to be core to a lot of the grand challenge engineering we're doing, you need good tools in order to do machine learning. And so we've been working on various tools over the last kind of 8 or 9 years. And about 5 years ago, we released a system called TensorFlow, which is kind of a system that we designed to make us able to try different machine learning research ideas, but also then take those ideas and put them in all the different places that machine learning models might want to run. Like you can run them on large data center systems, you can run them on small mobile phones, and so on. And it was released in the end of 2015, and it's been a pretty popular GitHub repository since we released it. And this is the kind of number of GitHub stars, which is one measure of interest in different GitHub repositories. And TensorFlow you see in the green line there, and several other popular machine learning toolkits you see in the other lines. And what we hoped would happen when we released TensorFlow was that it would create a sort of vibrant open source community around it. And so, in fact, that has actually happened, which is great. So we have about 2,600 contributors to the code, only a third of which are Google employees. The rest are sort of other people out in different industries, different universities, individuals, and so on. And the system's been downloaded 130 million times, which is a staggering amount for a relatively obscure kind of machine learning programming toolkit. And people have done interesting things. So here's an example of a company in the Netherlands that builds fitness sensors for cows, and they use TensorFlow to analyze the sort of accelerometer data from the fitness sensor. They can tell, which cow is limping today and wasn't limping yesterday, so maybe you should go have them checked out. There's a group related to agriculture. There's a group at Penn State University in the United States and the International Institute of Tropical Agriculture in Tanzania that has put together some really nice work on doing image-based disease detection for cassava plants, which is a very important staple crop in much of the tropics. So something like it's the third most popular source of carbohydrates in the tropics for people who live there. So it's very important, and lots of it is grown by small farmers who don't necessarily know all the different diseases that a cassava plant can contract. And so by taking a picture of a sort of that disease-looking plant or leaf, and the system can then use machine learning and analyze what's wrong with the plant and tell you how to treat it. So one of the things that has really contributed to this rise of deep learning is the more computational power that we started to have available in about 2008, 2009. We've suddenly had enough to start to do interesting things. But the trend has continued, and the more computational power we seem to have with deep learning models, the more interesting things we can do, and the more powerful and accurate the models get that we try to train. And so really, one of the things we focused on at Google is how do we actually rethink computer architecture around the kinds of computations we want to do in deep learning. And deep learning has two really interesting properties that make it different than sort of handwritten C++ code that has lots of if-then statements in it and so on. The first is that reduced precision seems to be totally fine. So 1 or 2 decimal digits of precision is great. You don't need 6 or 7 decimal digits. And the second is that all of the models I've shown you are different compositions of just a handful of specific kinds of linear algebra operations, things like matrix multiplies, vector dot products, other kinds of things like that. And so if you look at these characteristics and you say to yourself, great, I'm going to build a computer, but the only thing it's going to do is reduce precision linear algebra pretty much. And I'm going to make the computer really efficient for that. Then you come up with something that is what we call a tensor processing unit. And so this is the second generation of our tensor processing unit, which was sort of developed about 4 years ago, I guess. And what you see is a board with 4 different chips on it. And if we look inside one of those chips, you can see it's really specially tailored to do linear algebra. Unlike traditional processors, which have branch predictors and lots of kinds of caches and TLBs and all kinds of crazy things, This thing has a giant, it has 2 cores. Each core has a giant matrix multiply unit that can do 128 by 128 matrix multiply every clock cycle. It has some scalar and vector units for things that are not matrix multiplies, if you really must. And then it has some high bandwidth memory, so super high speed memory, so that you can get data in and out to the matrix multiply units. And that's it. That's literally a really simple linear algebra accelerator. And these things are really great for machine learning. The 3rd generation, you see on the bottom there, that adds, it's sort of similar chip with some, additional improvements. And we added water cooling, so we actually have water pipes that go directly to the surface of the chip, which is always exciting in your computer architecture. And all of these systems are designed to be connected together into larger configurations that we call pods. So the 2nd generation pod was 256 of those chips with 11.5 petaflops of compute. 3rd generation is more than 100 petaflops, all connected together, 1,024 chips. And these are also available through our cloud services. And we can actually connect together multiple pods, it turns out. So there's a machine learning benchmark called MLPerf that where people sort of test different kinds of hardware configurations to see how fast it can train machine learning models of various kinds. And so MLPerf is sort of like SpecInt or SpecFP were maybe 10 or 15 years ago for comparing CPU performance. This is for comparing machine learning performance. And MLPerf results came out about a month and a half ago for MLPerf 0.7. And these TPU pod systems actually really did extremely well. So these are the fastest results that we showed in the blue, and the 2nd place competitors in the gray, normalized to 1. So we're between 1.3 and 2.8x faster in 6 of the 8 benchmarks. And it's also worth pointing out that these benchmarks are now getting pretty small for the amount of computing hardware here. So each of the 4 benchmarks listed here finished in less than 28 seconds. So you can train a ResNet model from scratch in less than 28 seconds on one of these systems, which is great for experimental throughput. You have an idea, you want to try it, you'd really rather that idea give you results in a minute rather than many, many hours or days. And so that makes researchers more productive. We also have a new generation chip that we gave an early peek at in small scale setups of up to 64 chips. And that chip is going to be, between 2.2 and 3.7x faster than the TPU v3 on a chip-to-chip basis. So we're pretty excited about that. We're also working on very small scale chips for mobile devices because you want machine learning algorithms that can run efficiently on your phone, and so you want the same kind of linear algebra accelerators to be built into your phone system on a chip processor. Okay, in the last bit, I'd like to close with what's wrong with how we do machine learning today. So the current way that you solve a task with machine learning is you have some machine learning expertise, some human who knows a lot about machine learning, maybe they've taken a bunch of classes like yourselves, and then you have a model and you initialize it with random floating point numbers. So you literally exercise your random floating point generator, random number generator, and that's what you start with. And then you add data, and then you make little adjustments in the learning process to the random floating point numbers to gradually get better and better results on the task you care about, and you hopefully get a solution. Now, you can use a technique called AutoML, where a higher level ML algorithm actually performs many, many experiments in an automated way in order to get to a good solution. So there, you take data and compute, and you still have the random number generator, but now at least you have an automated algorithm that is trying lots of different experiments, trying different variations in a similar way to how a human machine learning expert would do. And you, again, hopefully get to a good solution. And in fact, you can get to better solutions in many cases than human machine learning experts, simply because the computer can try more experiments in a given amount of time than a human can sort of absorb and try. But a problem with this is you still start with little to no knowledge about the world, right? You're initializing the world's knowledge with a random floating point number generator. And new problems therefore need significant data compute. I would liken this to every time you solve a new problem, you're forgetting your entire education and you're starting over and having to relearn everything that you learned in school in order to solve a new problem. And that seems kind of crazy. So sometimes we use machine learning approaches like transfer learning, where you take a related problem that you've already trained a model on and you start training with that instead of starting from scratch, or multitask learning, where you take a few related tasks and you kind of bundle those together and train the system to simultaneously learn to do many of these tasks. But usually many is not very many. It's usually, you know, multitask learning of 5 or 10 things, not of hundreds of thousands or millions of tasks. So I think we can do better. And this is a direction that I'm pretty excited about and that we're exploring at Google Research. So here's the vision. What do we want? We want a large model, sparsely activated, so similar to the mixture of experts style work. We don't want to activate the entire model in every example. We'd like a single model that does many tasks rather than separate models for every new task we care about. We'd like to dynamically learn and grow different ways through the model for new tasks. And we'd like the model architectures to adapt as needed, kind of automatically. And adding new tasks can leverage the existing skills and representations built up from the tasks we already know how to do. So here's a kind of cartoonish diagram of where I think we're headed, which is we have a system like this that already knows how to do several tasks. And so it has different parts of the model that it likes to activate for different tasks. That's what you see by the line going from the task input to the task output. And it's built out of components. So some piece of a machine learning model with some state and operations. It might be, you know, a few layers of some transformer model, or it might be a convolutional piece of a vision model. And now we add a new task, this purple thing. So let me add that again. There we go. And so we can do some automated search over possible components that might help us with this new task. So maybe we find that these two components that this red line goes through are actually really good at getting us to have pretty accurate results for this new task. But we might want the task to be more accurate. And so we might want to add some capacity to the model and add a new component that is initially focused on solving this new task, the new purple one. And so now we have a model where we've added this new component and it's helped us get into a better state for this new task. Now notice that this new component can be used for solving other tasks as well, or maybe even helping us with tasks we already know how to do. And each one of these components might be running some architectural search in order to find, you know, what architectures are really effective for the kinds of things that are flowing through it. Okay, so I think that's an interesting direction and where we might be headed. I just want to touch on thoughtful use of AI in society. So there are a lot of issues that Manish kind of touched on in the beginning of bias and fairness in machine learning models, safety in how machine learning models are deployed. And it's really important that you consider these as you consider how machine learning should be used. And so we, a couple of years ago, published a set of principles by which we think about using machine learning. And we want to uphold these principles in all the uses of machine learning that we have. And it's worth pointing out that many of these are sort of active areas of research. So like the area of unfair bias and avoiding bias is like an entire research field on its own. And so this is just a sampling of the kinds of work we're doing in some of these spaces related to fairness, bias, privacy, and or safety. You know, I don't want you to read all the titles here, but it's like a pretty comprehensive set of work that is going on throughout our research organization. And with that, I'm going to turn it back over to Manish, I guess. And thank you very much for listening. I can't see any of you, so I hope you're all still awake. And with that, I will stop presenting my slides and come back.
So thanks a lot, Jeff. The students are not only awake, they're posting lots and lots of questions on Dory. So we'll bring up Dory and uh, start asking you to answer some of these questions. So they relate from all the way from advice to technical questions. So the first question that people have is, what advice would you give to young researchers just starting out?
Yeah, I mean, this is like a really exciting time in the fields of computing and in machine learning, which I guess all of you are interested in. I think one piece of advice is focus on problems that you're personally interested in and that matter. So take ambitious problems, try to make progress on them, find ones that are interesting to you. One piece of advice, I think, sometimes as a researcher, it's really important to really deeply understand particular areas that are very adjacent to the work you're doing. But another general piece of advice that is useful is to kind of pay attention to lots of other little things where you don't necessarily need to understand them all deeply. So skimming 10 papers in completely different areas than you're working in may trigger ideas down the road, or reading 100 abstracts rather than reading one paper in depth is generally a good idea, because that gives you this kind of constellation of techniques and ideas that you've kind of seen but haven't really fully digested, and that you can then kind of combine together or adapt to a new problem you're trying to solve. And that I think is a good general approach.
Great. And the next one is again a more specific version of that question, given that there's so much research being published, and along with your own work, how do you go about reading new research papers, even if it's not complete reading? And you refer to, again, read 100 abstracts instead of only that one paper. Any advice about that?
Yeah, I mean, I think one of the great things is because people are active in various kinds of social media, there's actually quite a lot of discussion of machine learning papers on Twitter, for example. And so I often come across interesting new papers from things that people have referenced on Twitter. It's like, hey, I just put up this new paper on arXiv and people are discussing it. And often you can even get the gist of the idea of the paper from the Twitter discussion. So you're just reading, literally like 10 tweets about it and people asking questions. And you're like, oh, okay, I see they're doing transformers with this kind of wrinkle. I kind of have a sense of that. I don't necessarily understand all the details because I haven't read the paper in detail, but I now have filed this away and can sort of reference that if I needed to. If I really wanted to know the details, I could go look up the paper.
Great. And if you were a grad student today, which research discipline would you choose?
Well, I like machine learning because I think it's going to be, really impactful across a huge range of different areas of human endeavor. Like you saw the list of grand challenges, and I think machine learning is really going to help us tackle most of those. I think having a good fundamental understanding of computers and computer systems combined with machine learning is a really amazing combination. Some of the biggest progress we've made in ML research in our own environment at Google is the coupling of large-scale computer systems work with machine learning algorithm work. And often, no individual has both of those skills. That's a pretty rare combination. So we often make teams where some of the people have more ML algorithmic skill and some have more computer systems building skills and do things together. That's a perfectly valid way to do kind of interdisciplinary work. But it's even better if the same person has both of those kinds of skills, because they're very adaptable then. You can go solve new machine learning problems. You can build computer systems that use machine learning to do all kinds of cool things, and so on.
And Jeff, on that note, I was talking to some people earlier, and they weren't aware that you had done your graduate studies in compilers, that research, because they knew that didn't come in the way of you making all these advances first in MapReduce, distributed computing, and then machine learning. So I guess you kept learning new things.
Yeah, I like to dabble. I mean, I think that the thing I just said of a team coming together with many different kinds of expertise on the team, you should try to find yourselves in situations where that's happening throughout your career, because if you get 4 or 5 people working together and they each know different things than you know, some of what they know rubs off on you and some of what you know rubs off on them. And then even if you stop working together after you finish your project or whatever, you now know something about their area of expertise, and you can go ask intelligent questions or understand kind of a basic paper in that new area because you've been kind of hanging out with this, statistician or, ophthalmologist or whatever it is.
Okay. So what's the craziest AI application that you think the world might see in the future? Something that looks unrealistic now, but could be possible.
I am really hopeful that at some point we will get to a system that can absorb the world's knowledge and can then develop new hypotheses and test them and develop new scientific discoveries as a result of that. Like, that would be pretty amazing. It would require the ability to integrate and synthesize tons and tons of information about what we know about the world already, and raw data about the world, and to make hypotheses that are interesting, and to then be able to sort of do experiments or make observations and solve that. That would be pretty phenomenal.
Thanks, Jeff. Great food for thought for some of our students. Maybe they can start working on this. So huge general models like GPT-3 from OpenAI currently cost huge amounts of to be trained. And I sometimes have to run my models for some duration to iron out the hyperparameters. If these running costs are so high, how do research teams work with hyperparameter tuning in a feasible manner?
Yeah, so a lot of different approaches here. I think one of the most important ones is if you have a very large data set or a large model, you want to be able to kind of scale that down into something that you can do most of your hyperparameter and algorithmic tuning work on a smaller scale version. So think something that is, runs in a few hours or is 1% of the size of the ultimate problem that you're trying to solve, and do most of your iteration on that. Then scale that up to something that's 10% of the size and do a little bit of revision and tuning on that, and then scale up to the final size, and then you hopefully run once or maybe twice on that and not more, because as you say, it is pretty infeasible to run the largest scale things many, many times.
Okay. So black box nature, again, of deep learning models makes it difficult to deploy in safety critical systems. So I'm curious to know what steps is Google AI taking towards verification and interpretability to use AI safely in healthcare, society, and other domains.
Yeah, I actually dropped some of the content I had on this topic from the talk because it's a bit shorter talk. But basically, I think these are really important issues. I think the reputation of neural nets as a complete black box is a bit old, because there's actually been a fair amount of progress on various kinds of visualization and understandability and interpretability techniques for machine learning models, particularly deep learning models, that enables people to get some insights into why is it making this kind of decision. So in the ophthalmology example, we actually have a visualizer that can show an ophthalmologist, we think this is a 2, not a 3 on the grading scale, and here's the parts of the eye that are making us think that. And so that's the kind of thing you need to be able to build and use in a real deployed system in a setting like healthcare or other things, where you do want kind of a human in the loop, and you want the system and the human to collectively come up with a really good assessment of the situation. And so you really need that kind of interpretability and good visualization, good UI design, and so on really are paramount there.
Okay. So Jeff Dean can optimize a piece of hardware by dropping it on the floor. Is that true? More seriously, can you give some anecdotal experiences of your journey from being a college student to the great leader at Google Research AI? What obstacles have you faced, and how much expectations did you have for yourself?
I think one of the things I was trying to do when I finished my undergraduate was to figure out what I should study in graduate school. So I was actually considering, I had a dual degree as an undergrad in economics and computer science. And so I was debating going to graduate school in economics or computer science. Ultimately, I decided computing really had the ability to impact way more people. And so I decided to study computer science. But I think one of the things that has been true throughout my career is the willingness to kind of dive into problems where I really don't know very much, or where I have some of the skills needed to kind of look at the problem, but where, I don't have the full set of skills, and then to work with people who know different things than I know. And so I think that is something that some people just are unwilling to put themselves in that situation, but I would encourage you. It feels uncomfortable, and you'll ask stupid questions about some other topic you don't know very much about, but that is the way you learn really fast. And so I think that's something that I'm able to now look at a new problem and draw on a background of similar kinds of things that I've looked at, so that I can at least know a little bit about what's going on.
Okay, so which ML would you prefer? Theoretically elegant but too sensitive to hyperparameters, or works well in practice but poor theoretical backing? And what's the most used interpretability, explainability algorithm at Google?
I think I'm a pragmatist, so I like the works well in practice but not theoretically grounded, because I think, actually there's a good analogy here, which is a lot of the optimization techniques that we use in deep learning are trying to optimize these highly non-convex functions. And so if you'd ask theoretical mathematicians, what theoretical properties can you tell me about these like million-dimensional non-convex functions? 15 years ago, most of them would say, well, we don't really focus on that. We do convex functions, and we can tell you lots of stuff about that. But I think the pragmatic practical realities that deep learning models actually started to solve real problems made it so that the theoretical community suddenly started to turn their attention to, non-convex functions are really a pain, and we don't understand very much about them. Maybe we should start to pay attention to them and understand more about their properties. And so I kind of feel like a lot of innovation comes from the pragmatic, practical things that are not necessarily fully theoretically understood coming first, and then other things coming later, the theoretical understanding. But there's tons of innovations that have happened in the reverse. So either one is great.
Great point, Jeff. I know a lot of my computer science theory friends who have now started paying attention to machine learning.
I skipped the second part. I think one of the interpretability techniques is actually the attention mechanism in transformer models actually turns out to be surprisingly good at showing you what kinds of things the model is paying attention to in the input.
Okay, so again, back to a personal question. The friendship that made Google huge, a story of Sanjay and Jeff Dean's friendship, which helped Google survive at the time of emergency. Can you tell us more about such incidents and stories of friendship at Google?
Yeah, I mean, I'll just tell you, like, Sanjay is an incredibly great colleague, and we still work together. We spend Mondays and Fridays pair programming virtually now in COVID situation. So like we share our screen, and like he usually types and I sort of have a second screen, and I'm doing stuff on the side, and we're talking via video chat. But I think one of the things I would say is that pair programming is really I find it an incredibly effective technique, because you have a colleague that you're sitting with, and every decision you're making, you're suddenly having this conversation with someone and saying, well, what if we did it this way? How about that way? Have we thought about this? And I just find you get to better overall decisions, because it's very easy for a single individual to get 9 out of the 10 things right, but overlook something in the 10th decision. And if you have 2 people there, the software that you produce and the interfaces you design and those kinds of things just generally seem to be higher quality. So, that's one kind of friendship. I think at Google, I have a regular crew of people that we go to the espresso machine every morning at 9:07. If you're not there at 9:07, you miss the coffee train. And we go and collectively make, 8 cappuccinos for the 8 of us. We each have different jobs. Someone grinds the beans, someone packs the espresso, someone froths the milk, someone lays out the cups. It's like a little espresso assembly line, cappuccino assembly line. And that's kind of fun. We chat about whatever, sometimes technical work topics, sometimes like, oh, what are you doing this weekend? Or read any good books or whatever. It's important to have fun at work as well. So.
Absolutely. So if you were an AI algorithm for a day, which one would you pick yourself to be?
Oh, wow. I could say Transformer if you've been paying attention.
So I don't know if this was inspired by another of those Jeff Dean facts. Jeff Dean doesn't really exist. He's an AI program invented by Jeff Dean. So anyways, so working with neural networks feels more like an art and experience-based intuitive modeling, like the ingenuity utilized for Lego houses rather than science. To what extent is this true?
Yeah, I loved Legos as a kid, so maybe this is why I like neural networks. I do think there is some truth to that. And if you look at kind of I didn't talk about it in this talk, but some of the kind of neural architecture search and automated machine learning methods, a lot of those things are sort of automated ways of putting together Lego blocks or sort of different neural network components in different ways and trying lots of different ways to assemble complicated structures out of simple pieces. And I think that is one of the intuitive beauties of deep learning, is that it's all composed of a relatively small set of primitive operations strung together in different ways. And that, I think, means that you can build customized hardware that is specialized to those handful of different operations. You can assemble them in different ways and do interesting things. You can have different inputs and have the model do completely different things, speech recognition or language translation or computer vision, with different arrangements of similar pieces.
So given that most research roles in industry labs require a PhD, how do you see undergrads and master students contributing to the work done at the labs?
Yeah, so most of our people who are officially in research scientist roles do have PhDs, probably like 95% of them or something. I don't know the exact number. But we definitely have quite a lot of undergraduates and master's students who are working full-time now. And they often are kind of research engineers. They're teammates on the same teams as research scientists. And they kind of collaborate together on projects. We often have people as interns who are undergraduates or master's students. We have an AI residency program where we sort of have people come spend a year with us who want to learn how to do research. And there are many different stages of their career. Some are fresh out of an undergraduate or master's program. Some already have PhDs, often in other fields, and have now wanted to switch into doing machine learning research. And so we mentor those people. Sometimes they stay on as full-time employees. Sometimes they go off to graduate school and get PhDs. There's lots of ways to get involved in the research process, even if you don't necessarily have a PhD yet or don't have an interest in getting one.
Thanks. So what are the top 3 habits that you picked up as a grad student in order to become a better researcher that you still continue to do?
All right. I think one is being able to find problems that are ambitious but are solvable in a reasonable amount of time. So I think there's a delicate balance between picking problems that are not ambitious enough because you can solve them, versus picking ones that I find are too far out, like problems where it's going to take 25 years to solve. I don't quite have the vision to say what is the exact path we should use to get to the solution of a 25-year problem. I find I kind of like to meander along a course of what are the next things we can do in a sort of 2, 3, 4 year time frame. and work on those. And then that kind of reveals the next set of interesting problems to me. So that's one. I think being able to work with people who have different kinds of expertise and learn from each other is another one. And I don't know, picking great colleagues who know more than I do.
Okay, thanks. So what's the one thing you would have told your younger self to do or do differently had you been able to time travel? And what would you tell us, especially those still pursuing their bachelor's and not sure about where they want to go in terms of their career?
Well, embarrassingly, I've never taken a machine learning course, so I would take a machine learning course. That seems like a fine thing to do. I think college is a great time to take some classes that are deeply in things you're interested in, but it's also a time where you can, take a few classes that are kind of outside your comfort zone, outside something you think you might like, but you don't necessarily think is going to be right in line with what you're going to do in your career. It's a good time to kind of explore different areas. Sometimes you might find something that is pretty cool and interesting, even if it's kind of very different than a lot of your other classes.
So while AI is powerful, it is difficult to infuse human reflexes, emotions, and sentiments in it. For example, in an autonomous vehicle, how should the AI decide whose safety to prioritize, the pedestrian or the driver? For a human driver, it's an obvious decision if your family is in the car as well.
Yeah, I mean, I think none of these decisions are easy. I mean, this is kind of a bit of a false way of stating it, because I don't think you're having machine learning models that are making ethical trade-offs like that. What they're trying to do is be as safe as possible given the environment and the surrounding actors in that environment. And honestly, I think when autonomous vehicles get onto the road, they're going to be way safer than human drivers, because they're getting sensor input from a 360-degree field of view LiDAR. They're getting input from 18 cameras on the car, and they can see in all directions. And so really, I think the important thing to realize is even though there will be accidents with autonomous vehicles, the world is, our autonomous vehicles at Google have actually been in a couple of accidents, almost all of which are a few accidents, all of which are other cars rear-ending them for the most part. And so I think it's really important to realize that these systems are going to be different. They're sensing all the time and making decisions that maximize safety of the overall environment, and they're going to be way better than human drivers. That's my belief.
Thanks. So what are your thoughts on gradient-free learning?
Yeah, I don't quite know what you are referring to, but I do think things like evolutionary algorithms are quite interesting. I think, having a population and having slight mutations is definitely like another thing that we know has produced really interesting things in the world. Lots of interesting animals and plants and all kinds of things work because they come from a large population that has evolved over time. And I think evolutionary algorithms have the potential to be a key component of how we might build sort of really intelligent systems. I'm not sure pure gradient methods alone are going to be sufficient to get us to where we want to go, and they have different strengths and weaknesses compared to evolutionary algorithms.
So machine learning models can have inherent biases. How does Google ensure it's not discriminating against anyone when incorporating them?
Yeah, so we generally have a collection of techniques that we use so we can evaluate how is the model performing on particular subsets of a population and make sure that the performance is roughly similar in, say, different subgroups, say gender or race or whatever it is. that's an important evaluation you want to make in any machine learning scenario, that's particularly ones dealing with human data or making decisions on behalf of humans. There's a whole collection of literature about building less biased machine learning algorithms. There's with Google authors, so you can search for that and find one by Google researchers. There's one by Moritz Hart and others, who is a part-time Googler and Berkeley faculty member, called Equality of Opportunity in Machine Learning Models, or something kind of like that. So that's one technique. It's a mathematical technique you can make to any machine learning model that you can then adjust the outputs in a way that prevents certain kinds of bias that you are looking for.
Okay. So as AI systems, oh, sorry, this is a repeat. I think we should go to the next one.
Okay.
So Jeff Dean suggested that 100x computational power could replace the need for machine learning expertise. My question is, can the massive amount of computational power really replace machine learning expertise?
Yeah, I took out the whole section on AutoML and neural architecture search from this talk. So I don't think it will completely replace human ingenuity and all machine learning expertise, but I will say that if you look at the best computer vision models these days, for example, they are all architectures designed by neural architecture search-like algorithms, where a outer algorithm is essentially trying these different ways of assembling Lego blocks and comes up with architectures that are much, much better in terms of accuracy and accuracy per computational operation than the best human experts in the world at computer vision, model and machine learning. And so for certain subsets of what a machine learning expert does, the kinds of things where you're searching some large space of possibilities, and you can define the search space so that it's pretty big but not too big, like 10 to the 30th is good, 10 to the 60th is too big a space to really have these techniques be effective, 10 to the 5th is way too small, then the system can find really interesting combinations in a space the size of 10 to the 30th that humans just will never stumble upon, because we can't run experiments and understand the results of those experiments and absorb them and figure out the next set of experiments to try as fast as a machine that can automate that.
Okay, thanks. We'll take one last question. Can you describe a day in your life? Does being at such a high position come with a lot of sacrifices, as it's mostly perceived, and mechanical lifestyle?
Yeah, I mean, I guess I am a somewhat unusual person in that I am now managing a fairly large number of people, about 4,500. I also manage our health organization in addition to the research organization. But I still carve out 2 days to basically write code and do development on a project that I'm working on with a bunch of other people. Actually, it's called Pathways. It's sort of the cartoonish diagram towards the end of my talk. How do we build these really large integrated machine learning systems with components? And so depending on the day looks quite different. If it's Tuesday, Wednesday, or Thursday, then I have a lot of kind of reviews of different kinds of research projects that are going on in the research organization that I'm not necessarily personally involved in, but I can provide input and suggestions and so on. Or I'm making decisions about, like, how many TPUs do we need to buy in 2021 for our own internal research purposes. And if it's a Monday or Friday, then I'm pair programming with Sanjay on the Pathways project that we're collectively working on with 8 or 9 people, and going to technical meetings about that. Day always involves lots of espresso and cappuccino. Now that I'm working from home, it's kind of weird. I kind of wander out of the office where I'm working into the kitchen and stare at my wife, and we kind of look at each other. We're like, what should we have for lunch today? Which is kind of nice. It's a little different, and if I was at work, we'd grab a bunch of colleagues and we'd go into the cafeteria and have lunch together and then go back to work.
So Jeff, there are tons of questions again, but for COVID, had you been around, of course, you would have been around physically. I think you would have spent the entire day with students, just
My
asking,
apologies.
but
So
I know it's getting late for you. We really appreciate giving such a fantastic talk and sharing all of your pearls of wisdom with the students. Hopefully, they'll make you proud one day. They'll point to hopefully this talk and some of your remarks as having inspired them, maybe to work on some of those crazy AI applications. So thank you so much for taking the time. And again, we look forward to seeing you interact with the students another time in the
yes,
future.
thank you very much. And I'm sorry I couldn't be there in person. Goodbye. Good night.